Hey everybody, this video is going to talk about solving problems, solving kinematic problems. So it won't be that long. It's going to go through the kinematic equations and talk a little bit about some different ways to approach these. So motion with constant acceleration, we use generally we use a velocity graph to find the acceleration. So you take the rise over run. This is really straightforward. We've talked about this with position graphs. It's no different. From this equation, we rearrange to solve for the final velocity. So when we do that, final velocity equals initial velocity plus acceleration times that change in time. And so this is our first equation, and mentioned this before, but this little x, this subscript x here, and here in the acceleration and this initial velocity, they are just referencing the horizontal direction. We may be going in many other directions, so as it states right here, it could be any axis. So generally you will not see that little subscript. When we use a velocity graph to find displacement, we take the area underneath. All right. And if you rearrange that equation on the previous page, you can figure out that this side of this triangle is equal to A times T. You're just rearranging the VF minus VI, and that equals A times T. So if you keep this side as A times T, and this side is delta T, you end up with 1/2 A times delta T squared for the area of this triangle. And then for this one, you're looking at the initial velocity times the change in time. So VI times delta T. And you're adding these two together. So when you do that, you have this equation, VIT plus 1/2 AT squared, and that equals the combination of this. These two variables would be delta X. All right, so oftentimes I will write this equation, or you will see this equation as this, VIT plus 1/2 AT squared. I tend to lose the deltas for the t's, and you will see that quite often when you're looking elsewhere, these kinematic equations. So here's our second kinematic equation. This is the way it's written on the AP equation sheet, which I will make sure is posted on the website or on Schoology somewhere. I'm not going to go through and combine these. You can find plenty of derivations of these, but you combine them, substitute some things in, and you end up with this third equation, VF squared equals VI squared plus 2A delta X. All right, so those really quick are the three kinematics equations. Sometimes you see a fourth, which really just average velocity, but these are the main ones. And so when we're using these, here's the whole list of them. When we're using these, we they can help us solve problems really, really nicely. So when solving a problem, we start with the 5 variables. So these are the kinematics variables, VI, VF, delta X, A, and T. I'm going to put this is vector notation up top here. There we go. Pretend that's a vector notation. Good. So you drive in your car at 15 meters per second, which is just under 35 miles per hour. You see a ball roll into the street, and you have to come to a stop. So you stop as quickly as you can. It takes 1.5 seconds. How far does your car travel while you're braking? All right. So we need to figure out which variables we have, which one we need to find, and then apply the equation to find the one we need. So the first thing that you should do with all of these problems, even if they are easy, super duper easy, draw a quick picture or a diagram. So there's one already here, and I'll draw one in the next problem, but this one we have a motion diagram showing the velocity vectors and the acceleration vector. Not a bad idea. Even better probably is to sketch a velocity graph. You don't always have to put numbers in it, but you certainly can. It could help you double check your answer in some cases. So let's see here. So we have 15 meters per second. We have 1.5 seconds. And those are all the numbers we're given. So we have to find 3. If we have 3, we can solve for the other 2 no matter what. So let's see. You're driving in your car at 15 meters per second. So that sounds like the initial velocity to me. Your car comes to a stop in 1.5 seconds. So that's how long the motion takes. And it says it comes to a stop. So that means that your final velocity is 0. All right. How far does your car travel as you brake? So that sounds like, what is your displacement? It doesn't ask about the acceleration. We could certainly solve for it, but we don't have to. So let me, I'll write these really quick. Vf equals Vi plus A times T. V squared equals Vi squared plus 2A delta X. And then delta X equals Vi times T plus 1/2 A T squared. All right, so which one of these equations works? Well, let's see. We want to find delta X. So this first one doesn't have delta X in it at all. So, but we do have everything except that acceleration. Okay, so we could find acceleration, but we don't need to right now. All right, second one. Now it has delta X, that's good. But it also doesn't have acceleration. So there's 2 unknowns. We can't use that to solve. And then this one has delta X, good, but it also has A. So again, 2 unknowns we can't solve. But what we can do is we can use this one to solve for A. And I'm going to rearrange that. Remember, this is the general equation for acceleration anyway. So rearrange your variables. Okay, final velocity is 0 minus 15 divided by time 1.5 seconds. So the acceleration, negative 15 divided by 1.5, that's a negative 10 meters per second squared. Now, you could calculate the slope from this graph down here. You should know that it's negative acceleration based on this diagram right here. But it's not asking for the acceleration, right? It's asking for the displacement. So we now want to solve for displacement. So you could use this equation. You could really use any of the equations. All right. It's already isolated for delta X, 15 meters per second times 1.5 seconds plus 1/2 times negative 10. We're running out of room here. 1.5 seconds squared. And so when you go through that, you end up with a displacement of 11.3 meters. Now, if we're rounding to sig figs, how many sig figs would there be? There'd be 2. So we would round this to 11 meters. And that would be your final answer. Now, always good to go back and check. Let's see, here it is running through. You can take a look. Does this answer make sense? It's about 35 feet, right? You know, there's about 3 feet in a meter, a little bit more. But you should always go back and double check and say, does my answer make sense? If you had gotten an answer of 50 or 60 meters, and you say, wait a minute, that's like 100 feet, right? That's really far to slam on your brakes and go in 1.5 seconds. So think about that as you're going through problems. All right, Spud Webb. You might not know Spud Webb, but he was a really short basketball player, 5'7". He was in the NBA dunk contest. I want to say like late 80s, something like that. And he was a spokesperson for Reebok, and they came out with a shoe called the Reebok Pumps, and they were like the big deal. You put them on, you tied them up, and then squeezed a little button on the tongue, and it filled the shoe up with air. So he went out for the dunk contest, and he was getting ready to do his dunk, and he stopped, pumped his shoes up, and everybody went crazy, and then he went and did some nasty dunk. It was interesting. So he had a vertical leap of 110 centimeters. So we go through delta x, a, and t. And not to forget, I said we should do a little sketch. And believe me, I mention this all the time. I am not an artist. All right? So there's the hoop. All right, so let's say his vertical leap was somewhere. Well, we got to put it above the rim, right? I mean, this is, he was legit. He had some hops, so that would be our delta x. All right, does not need to be anything crazy, but there you go. You have something drawn, something to help you visualize. So let's talk about this. The only number here is 110 centimeters. Now that's a distance or a displacement, and if you were going to guess, that would be a good guess to put that in right there. We're going to convert that to meters. Now when you jump at your highest point, how fast are you going? Right? Think about that. As you jump up in the air, you slow down the whole way. So your final velocity is actually 0. And this final question, with what speed would he have to leave the ground? That means you were trying to find out the initial velocity. All right. So what else are we missing? Because there's only 2 numbers. I said we need 3. So what we're missing is what causes you to, as soon as you jump up in the air, why do you slow down? That's the question. Well, of course, it's the acceleration of gravity. If we make up the positive direction, down the negative direction, which is conventional, not always that way, we will say that gravity acts with an acceleration of negative 9.8 meters per second squared. And that is our third. And if you weren't sure about that, don't worry about it. We will talk about that more when we get to free fall next unit. So we want to find out VI. And if you're looking at your equations, once you look at them for a couple seconds, you'll realize that this is the equation to use. And we want to solve for VI. So we want to get VI by itself. VI squared equals VF squared minus 2A delta X. And now we can plug some stuff in. Okay. Now, of course, we have to do the square root of both sides to get rid of, because we don't want VI squared, we want VI. So VF is 0, so that's 0. So we're left with negative 2 times negative 9.8 meters per second squared times 1.10 meters. That's the displacement. We put that under the radical. And let's see, VI, there we go. And so when you multiply that through and take the square root, you get an initial velocity. And there we go. Initial velocity of 4.64 meters per second. If we look at sig figs, we should have 2 sig figs. 4.6 meters per second. And put a box around that. So that is the launch speed that he would have to leave the ground with in order to have a vertical leap of 110 centimeters. Okay, so sometimes we will use some quadratic relationships. We'll get into that later. And then the rest of this, I'm going to go through this just kind of quickly. You can go back through. These are just some general suggestions about how to solve these problems. Here's another example. I'm not going to go through and solve them, but it's all here. You can pause it.